Okay, now how do we define the one-sided limits in using precise definitions? Well, it's just similar to section 2.3. Okay, we say that f of x has a right-hand limit L at x equal to x sub 0 if we say that for every number epsilon greater than 0, again we find a delta greater than 0 such that, look at this, remember what we do is we give an epsilon and then we find a delta. But it's only on one side. Instead of a symmetric interval, instead of a symmetric open interval around x sub 0, here it's just a one-sided interval. Okay, where one endpoint would be x sub 0, the other endpoint, of course, would be x sub 0 plus delta. And in the same way, if this limit is L, then that other part of the interval is L plus epsilon. So this open interval is equivalent to this one. So if I pick out an x here, pick out an x, then the corresponding f of x will be within this distance right there. Okay? Now, same thing with left-hand limit L at x sub 0. It's the same thing. So here's our x sub 0, and you let your x's approach 0 coming from the left. Then, okay, you've got a different open interval where we will find the x's that will satisfy this epsilon inequality. Okay, it's the other end, so it'll be, this is equivalent to having an open interval from x sub 0 minus delta all the way to x sub 0. Okay, so it's just the other half of the symmetric open interval that we've looked at before. Again, you're given an epsilon, and then you project down and find the corresponding open interval that contains one endpoint instead is the x sub 0. But it's the same thing. Now, so here's another example of a function that has a one-sided limit as we look at the limit of the square root of x. As x approaches 0, coming from the right, of course. And we see here that it's equal to, as x approaches 0, from the right, the y values, right there, the y values approach 0. And again, if we want to solve for that f of x minus L inequality, epsilon inequality, we'll have the square root of x minus 0 is our L, is less than epsilon. So that means we take the square root of x, it's between epsilon, and look at this one, it's only from 0 to epsilon. We don't have a minus epsilon because it's just this part. Okay, so then we square everything, we get x is between 0 epsilon squared. Well, what is the delta that we want? Okay, the delta that we want is an open interval from where? From 0 to delta. Okay, this is this open interval from 0 to delta. So naturally, it's just a match-up right here. We choose delta to be equal to epsilon squared. Okay, so that if we choose this, then for all x's, such that if the x's are between 0 and epsilon squared, then it implies that the absolute value of square root of x minus 0 is less than epsilon. It's just, what we've done here is we have shown the proof of the limit of the square root of x as x approaches 0 coming from the right is equal to 0. Alright, here is a particular example where the limit on both sides do not exist, because if we take the limit of the sine of 1 over x, as x approaches 0 coming from the right, so here you've got your x's coming from the right. Notice how all these y values oscillate back and forth from -1 to 1. Okay, so it does not exist. Similarly, if we take the limit of the sine of 1 over x as x approaches 0 coming from the left, so you're just going in the same direction, and the left coming from the left. See how the y values kind of oscillate back and forth, so it does not converge at a common point. So again, this does not exist. So even if either side here is both sides do not exist, so the limit of y as x approaches 0 does not exist. Let's look at our last example, which is f of theta equal to sine theta over theta. And we have used this, we have shown using the sandwich theorem that the limit of sine theta over theta as theta approaches 0 is equal to 1 using the sandwich theorem. Now we can also look at it using the one-sided limits. So the the limit of sine of theta over theta as your theta approach 0 coming from the right. Let's see, here are my thetas, the angles, radian mode. Okay, they approach 0 coming from the right. The y values approach 1. Okay, let's look at the limit of sine of theta over theta as your theta gets closer to 0 from the left side. Okay, so I'm looking at all my theta, negative angles approaching 0 from the left. The y values approach 1. So using the one-sided limits, we can conclude that the limit of sine of theta over theta as theta approaches 0 is equal to 1. Woohoo! Theorem 7. This is an important theorem that we will use later on in solving problems. Just to remember, again, that the limit of sine theta over theta as theta approaches 0 is equal to 1. This is something that we need to commit to memory. You need to remember this because it'll be useful. Say, for example, we want to evaluate the limit of sine of 2 theta over 2 theta. Okay? As theta approaches 0, then see, as long as you have the same argument of the sine and the same expression at the bottom, that's equal to 1. Now, what about if we take the limit of the sine of 3x over x? Is that equal to 1? Well, in order for these to match, we need to multiply both the top and the bottom. Okay, we multiply both the top and the bottom by 3 and 3 here. Okay, so this is actually equal to the limit of 3 times sine of 3x. Remember, you can multiply this into the argument of sine x divided by 3x. This, of course, you can multiply because those are just algebraic terms. Now we take the limit as x approaches 0, and that's just equal to 3 times the limit of this ratio, and that's equal to 3 times 1, therefore it's equal to 3. Okay? So let's say, what is the limit of tangent of x over x as x approaches 0? Look at this. If we just evaluate the tangent of 0, that's just sine of 0 over cosine of 0, which is 0 over 1. So that's a 0 over 0. Okay? So if in such a way we can rewrite this in terms of sine x over x, then it will solve our problem. Well, let's take a look at the limit of, this time rewrite this as 1 over x times, now rewrite tangent as sine of x over cosine of x. And then just rearrange terms. So now I'm looking at the limit of sine of x, combine these two together, sine of x over x, times, now take 1 over cosine x. As x approaches 0, then this is equal to 1 times 1 over 1, and that's just equal to 1. So it turns out that the limit of the tangent of x over x is also equal to 1.